Here we go. What I'm going to do in this video is talk about the action potential in electrical terms. We're going to go over a lot of new terms today, but before we get on that train, let's talk about this experiment here. What we have is a segment of axon from a squid sitting in a saline solution. The exact formula for this solution is made to match seawater. We are all basically seawater inside with proteins mixed in there. Uh, so when you want to do an experiment like this, you need to match the environment of the axon to what it would normally experience in the body. Now we can get away with using these axons because an axon is an axon is an axon for the most part. Now, the fact that these are large is very helpful to us because getting these microelectrodes inside the cell is no easy feat. It's actually rather challenging, and the larger the axon, the easier your job is. And of course, squids are not endangered or anything like that. They're very, very plentiful. Now, this electrode is going to be connected to a voltmeter. A voltmeter is what it sounds like. It's a meter that can measure voltage. Now, what you will see as soon as the microelectrode pops through the membrane, as soon as it drops in, the voltmeter will jump and it will show a voltage of negative 70 millivolts. This number is very important. What this is the resting membrane potential. The resting membrane potential. Resting. What that refers to is when the cell is not doing anything, when the cell is simply at rest. There is a charge across the membrane such that inside the cell, sorry about that. Inside the cell, we are negative 70 millivolts compared to the outside of the cell. Now, one thing I'd like you to focus on is that this is a relative measure. Imagine you have your house here, and it's, let me see if this will help, and it's 70 degrees inside, and it's 50 degrees outside. If you stuck your voltmeter in here, if instead of temperature we're talking about voltage, you would read plus 20, because inside you're 20 more than outside. If you instead had your electrode outside, it would measure negative 20, right? It's relative. So what we're saying is inside compared to the outside is negative, and the charge is specifically negative 70 millivolts. Okay, now we're going to make the experiment a little more complicated. The right side of this setup is nothing new. It's exactly what we had in the prior slide. You have a recording electrode connected to a meter that can measure voltage. Sorry. This time, instead of using a voltmeter, we're using an oscilloscope. Oscilloscope is the same idea, records and displays a visual readout of the voltage inside your cell. Now, I think I've said this before, but for all of my drawings and my slides, the movement of charge information is going to be this way. As such, We have our recording electrode here, so behind it, we're going to implant a stimulating electrode. This electrode is going to be connected to an electrical stimulator. Through this electrical stimulator, we can provide electrical impulses to the axon. That will stimulate and move that stimulation down, and we can detect the effects of that stimulus at the recording electrode. Now, why do we use electrical stimulation? Well, let me see. Let's pretend I'm a Simpsons character. I can try to poke myself at a steady rate and at a steady intensity. And I'm trying my best right now. But as you can probably tell, this is not consistent enough. See, this is a physical stimulus if I were tapping my hand with my arm with my other finger. Instead of using that physical stimulus, we use an electrical stimulus because right after the point of the stimulus, it doesn't matter if it was my hand that was doing the stimulation or if it was an electrical charge, because from this point on, it all gets converted into electrical signal. So the rest of the cell has no idea whether it came from an actual stimulus like touch, or if we're talking about vision, something light getting into your eye, or if we're talking about hearing. Well, I'm getting carried away with the drawings here, huh? It doesn't matter. It all gets converted into electrical stimulation. On top of that, the electrical stimulator gives us incredible control. We can control the intensity. That's not an N, David. The intertrial interval, the frequency, and the number of stimuli. Perfectly perfectly controllable. Okay, in the next video we're gonna talk about this slide and go over a lot of terminology.